In this video, we're going to be talking about the acid-base properties of amines. Specifically, amines act as bases in solution. So we're going to be talking about what a base is, then we'll be talking about acid-base neutralization reactions, and then we will also talk about why pharmaceuticals are commonly sold as ammonium salts rather than amines. Let's talk about our properties. So what is a base? A base, by the Bronsted-Lowry definition of a base accepts an H+ ion. So how does it accept an H+ ion? The lone pair on nitrogen is what causes this molecule to act like a base. This lone pair of electron can attract a proton from water to the point where it kind of pulls it off. And so water here is going to lose a proton to the ammonia. And then we form our ammonium cation and a hydroxide anion. Base solutions have higher hydroxide ion concentrations than neutral solutions. So our primary amines do something similar. They have a lone pair that's going to attract this hydrogen off of water and give these electrons back to the oxygen. So we have our hydroxide ion form, and then we have our ammonium cation. So when we talk about acid and base strength, we are talking about how far does this reaction go towards the products. Strong bases really just completely form products. Strong bases are like NaOH, KOH, things with the hydroxide ion completely in the chemical formula. Amines, like ammonia, are weak bases. That means that this equilibrium is in effect. The forward reaction is happening, but the backwards reaction is also happening. That means that we have an appreciable amount of this molecule in its amine neutral form, and we don't have as much OH- ions as we do in a strong base solution. So ammonia, this is a weak base, and so we have mostly this. Then we have some of this. And so that makes it weak. Even though these are weak bases, they are the strongest organic base. That just means that all the other molecules are even worse at being bases. Since amines are bases, they can neutralize acids. Even though it's weak, it can neutralize a strong acid. So here is our base. We got 3 carbons on this, so this is a tertiary amine, and it's going to attract this hydrogen off of the acid and then give those electrons to the chlorine. And so the proton is transferred from the acid to the base, and so here we see the ammonium cation. The nitrogen is positively charged because we are forming that to be 4 bonds. And the chlorine ion here is the anion. And so this is an ionic salt. We have a cation and we have an anion. So together it would be neutral. It's just soluble, so it's dissolved. And so we have a soluble ionic salt. The charges here make them more water soluble than the neutral ion. And so this is more soluble because it is charged. Another thing to note is that when we did acid and base neutralization reactions with our carboxylic acids, we formed salt and water as products. Here there is no water formed. It's just acid plus base. Acid plus base equals salt. That's it. So here we are. Here's our amine. That's a hydrogen. The picture just below it made it cut off. HCl. That grabs that hydrogen, gives those chlorine its ions, and then we have an ammonium salt. And then this product here is more soluble because it's charged. Water loves charges. That's what the polar solvent is all about. So water loves charged things, and so that's going to make this way more water soluble than this. Those salts are also more soluble in bodily fluids. So here we are. If we are going to be naming our molecule, then we take when we name it, this is going to end the name with ammonium ion. So this was a thanamine, and so that becomes ethyl ammonium ion. This had 2 propyl groups on it, so its common name was dipropylamine. That's its common name. Its IUPAC name would include the propyl group as a substituent, so it'd be N-propyl propanamine as the IUPAC name, but whatever. It's going to have an ammonium ion in there. This is the pyridinium ion. So the ammonium salts, this is the cation. We always do cation followed by anion. And so this is tributyl ammonium chloride. And so this is more water soluble than the original. I realize I just did some common nomenclature on the past slide. It's not all in IUPAC. Oh, I didn't even notice that in my slides. All right, let's complete the acid-base reactions here. Go ahead and pause the video and try to draw the products of these reactions, and then unpause the video when you're ready to check your answers. Okay, so for our first one, it's really not going to change that much. So I can redraw the original molecule. And then instead of having just 1 hydrogen, I'm going to have 2 hydrogens, and that's going to give this nitrogen a total overall positive charge. And then its anion is going to be Cl-. And so that's going to hang out together. It's water soluble, so it's not going to be actually connected together in solution. All right, and then here we have our amine reacting with our carboxylic acid. And so our cation is going to have the I'm not going to try to draw the aromatic ring in there. So here's our nitrogen. This is a heterocyclic species. Our nitrogen is positively charged. I'm putting a circle around the charge to indicate it separate from these little plus signs of our products. And then this is CH3, CO, and then that O is negatively charged. So this is also a acetate salt. This is acetate ion, and that's pyridine, I think. So which of the following is more water soluble? Phenylphenirin, phenylephrine, or phenylephrine hydrochloride? So phenylephrine hydrochloride is more water soluble because it has charges. This is a nasal decongestant known as Sudafed, and it works amazing. And so this is a example of a pharmaceutical sold as a hydrochloride salt. You can see, I guess, the label here, phenylphedrine HCl. When you see it labeled like this, they're saying that they neutralized it with HCl. They're not selling you hydrochloric acid, and that they're selling you the salt made from those two things.